Now we're going to worry about Guy-Lussac's law. Okay? We started off with Boyle's law, which looked at pressure versus volume. Then we looked at Charles' law, which had volume versus temperature. And now we're going to look at Guy-Lussac's law, which is pressure versus temperature. And honestly, it's a lot like the last one we did. It's just that we got pressure on top instead of volume. And then we'll put all three of those laws together to make the combined gas law. One big law called combined gas law. Literally, it's called the combined gas law. Now, just like on the last one, temperature has to be in Kelvin. Okay, and Kelvin is the Celsius plus 273. So regardless of what information they give us in the problem, we have to make sure that it's in Kelvin, so we may have to switch that before we can do it. Just like Charles' law, notice our graph is just a straight line. So in general, as the pressure goes up, the temperature goes up, or as the temperature goes up, the pressure goes up. Either way, they go in the same direction. So this is also a direct relationship. Just as Charles' law was, the only one that was switched was Boyle's law. That was the inverse one where pressure went up but volume came down. So, okay, first thing, I see that my two temperatures are in Celsius, so we want to switch them. So T1 is going to be 25 degrees plus my 273. So there's my 298 K. And then my temperature 2, 919 degrees Celsius plus 273. Oops. And that one will be 1192 K. Always start off with my equation. P1 over T1 is P2 over T2. Now we go ahead and plug in our values. P1, we have 103 kPa. T1, we have 298 K. And then we want to find out the pressure, so that's P2, and then we have that over 1192 K. Solve this one, we just need the P2 by itself. So multiply both sides by the 1192 K. Here, of course, they'll get canceled. Does not matter the order. 1192 times 103 divided by the 298, and we end up with P2 equals 412 kPa. Okay. Now, please note the temperature went from 25 up to, over 900. So, that's almost 40 times. Not quite. The pressure, 4 times. Okay, so again, when the temperature is in Celsius, you're not going to see a direct relationship between them. You're only going to see that when we're in Kelvin. All right, so let's look at number 2 where everything's already in Kelvin. So we don't have to change them. They're already in Kelvin. P1 over T1 equals P2 over T2. Let's plug in our stuff. 6.54 kPa over 537 K equals new pressure P2 over 179 K. Just like in the previous problem, we're going to multiply both sides by the 179 K so that they get canceled over there. And in this case, P2 will equal 2.18 kPa. However, since I was in Kelvin in this case, notice this: 537 K over 179 K. Turns out that's 3. 6.54 kPa over 2.18 kPa. That's also 3. In other words, the 179 was a third of the 537. The 218 was a third of the 6.54. They go the same proportion. So if one drops down by 2/3, the other one dropped down by 2/3, as long as I'm in Kelvin. That's the key. Whereas in the previous example, okay, I increased nearly 40 times. The pressure did not go up 40 times because I had to make that switch from Celsius. So it doesn't really work in Celsius exactly. Yes, it goes up or it goes down, but not exactly. Whereas if I'm in Kelvin, hey, 3 times for both of them. All right, number 3. Pressure in a car tire is 2 atmospheres at 27 degrees. After a long drive, the pressure is 2.25 atmospheres. Yes?
For number 2, with the answer is P2 equals, yeah.
That's the answer, yes. P2 equals 2.18 kPa. So that was our answer. So again, number 3, the pressure in a car tire, 2 atmospheres at 27 degrees. After a long drive, the pressure is 2.25 atmospheres. What is the temperature in the tire at that point? Now, again, temperatures have to be in Kelvin. So we're going to have my T1, 27 degrees, add the 273. 300K. Let's go ahead and write down my equation. Always write down your equation. Someone asked last period, am I going to tell you which equation to use? No. I will put them all on the quiz, but you're going to have to figure out which one to use given the particular problem. But hey, if it's only got pressure and temperature in it, then you're going to want the equation that only has pressure and temperature. If it's got pressure and volume, then you want Boyle's law because that's the one that had pressure and volume in it. So really, it'll tell you what you need to know if you pay attention. All right, so 2 atmospheres. No problem that I'm in atmospheres instead of kPa as long as they're consistent. Over my 300K equals 2.25 atmospheres over T2. Now, the unknowns on the bottom, okay, so I can't solve it the way I did the ones up above. I'm going to do that cross multiply step. So multiply those 2 together, put it on the right. These 2 together, put it on the left. So I'm going to have my 2 atmospheres times T2 and my 2.25 atmospheres times the 300K. Now I can go ahead and solve it, divide both sides by the 2 atmospheres to make the T2 be by itself. Those will cancel. The atmosphere part will cancel over here on the right, and I'll be in K. So when I do that, when I go 2.25 times 300 and then divide by 2, I end up with 337.5 K. However, that's not going to be my final answer. Since my problem started in Celsius, that's how I want to end the problem, in the same units. I have to be in K to use the equation, but even if it didn't say specifically, I want to go back to Celsius because that's what my initial units were. So if I subtract my 273 from my 337, I end up with, my answer is 64.5 degrees Celsius. So it was at 27, more than 2 times bigger in Celsius, up to 64. My pressure just went up a little bit. But they do go in the same direction. Both went up. Any questions? Okay. Now, just as in previous papers, what if I don't actually have any numbers? How am I supposed to solve a problem like this? The Celsius temperature of a gas is cut in half. If the volume doesn't change, how does the pressure of the gas change? Okay, now I want Celsius temperature cut in half. So that's where I should start. What temperature? Heck, anything I want. So let's make it easy on ourselves. And I'll give you a hint of how to make it easy. If I look at problem 3, 27 plus 273, that gave me 300 K. That's a nice round number. So, let's do something like, maybe make, one of them, say 54. So I'm going to make T1 54, which is just double the 27. So now add my 273. And that'll be 327K. And as we have in the previous problem, since I've already got it solved for me, 27 degrees Celsius plus 273 will be 300K. So in Celsius, I go from 54 to 27. I cut it in half. Okay, now what about the volume? I don't have a volume, okay? The volume doesn't change, so I'm not worried about the volume. Volume doesn't change. How does the pressure change? I don't have a pressure. Well, let's just give us pressure. Let's just call it 2 atmospheres again. Okay, and see what happens to the pressure. So, P1 over T1 equals P2 over T2. So, 2 atmospheres at the 327K equals P2, don't know P2, over the 300K. They're always going to give us everything but one. So I have one pressure, those, in this case I'm making it up, but I have 3, just solve for the one that's missing. Both sides times the 300K. There they cancel. Over here, the K's cancel. So 300 times 2 divided by 327. And I end up with my P2 is 1.83 atmospheres. So it was at 2, and it's now at 1.83. Even though my temperature got cut in half, all I can say is pressure decreased. That's about all I can say. If I had picked different temperatures, if I had said made this one 200 and then the other one 100, it still would have gone down. It just would have been a different amount. Okay, that 273 factor always messes me up when I'm in Celsius. However, now let's look at problem 5. The Kelvin temperature is doubled while the volume is held constant. So the volume doesn't change. In all of these, the volume can't change. How does the pressure change? Now, hey, T1, 300K, T2, 600K. Again, we're just making them easy. And let's go ahead and make P1 be that 2 atmospheres. Okay, nice easy numbers. So, P1 over T1 equals P2 over T2. 2 atmospheres over 300 K equal P2, don't know P2, over 600 K. Multiply both sides by the 600 K. Cancel. 600 over 300 is just 2. 2 times 2. 4 atmospheres is P2. It was at 2, now it's at 4. So we can say exactly how it changed. If you double the Kelvin temperature, you double the pressure. If you cut the Kelvin temperature in half, you would have cut the pressure in half. So, almost identical to doing the problems for Charles' law. It's just this one had pressure and temperature instead of volume and temperature. Questions?
What if you had P2 instead of P1?
If I'd had that, so for example, if I'd had something like P1 over T1 equals P2 over T2, okay, and we went ahead and said double our temperature just like we did, okay, so imagine it looks like this now. P1 is over 300 K equals, let's say that the P2 was the 2 atmospheres this time, and T2 is the 600 K. Well, how would I solve this one? I want the P1 by itself, so I would, in this case, multiply both sides by the 300 K. So here again they cancel. Over here I have 300 over 600, which is a half. 2 times a half is 1. Or in other words, if P1, basically if P1 has half the pressure because it had half the temperature. So it should work both ways. Any other questions?